This is lesson Module 4, Lesson 5 on Symmetry. This is an honors only standard. Students, please go ahead and complete the warm-up on the screen. Teachers, pause the video now. Find the coordinates of the vertices of each image after the given rotation about the origin. Because our rotation is about the origin, our rules apply. So in this first example, when we rotate 90 degrees clockwise, our rule is x comma y, and then our x and y coordinates switch places, and we take the opposite sign of the x coordinate. If we rotate 90 degrees counterclockwise, that means this rule applies, x comma y. The x and y switch places, but we take the opposite sign of the y coordinate. And then if we rotate 180 degrees, the rule is x comma y. And we just take the opposite signs of each coordinate. The Florida's best standards for mathematics that we're going to be focusing on in this lesson is Geometric Reasoning 2.4. Determine symmetries of reflection, symmetries of rotation, and symmetries of translation of a geometric figure. Florida's mathematical thinking and reasoning standards. Demonstrate understanding by representing problems in multiple ways. Engage in discussions that reflect on the mathematical thinking of self and others, and use patterns and structure to help understand and connect mathematical concepts. Composition of transformations can be used to create patterns from polygons. A tessellation is a repeating pattern of one or more figures that covers a plane with no overlapping or empty spaces. A tessellation can be created by transforming the same figure or set of figures in a plane. The sum of the measures of the angles around a vertex of a tessellation is 360 degrees. And you can see that in this example where we have trapezoids and we have the 120 degree angle from the top part of our trapezoids and the 60 degree angles from the bottom part of our trapezoids. Together, all four of those angles add up to 360 degrees. Someone that you might have heard of before is an artist named M.C. Escher. He is actually famous for his art and using geometric tessellations to create amazing pictures. So if you're interested in tessellations, go check out M.C. Escher. A regular tessellation is formed by only one type of regular polygon. A regular polygon will tessellate if it has an interior angle measure that is a factor of 360 degrees. That means a factor of 360 degrees means you can take 360 and divide it by the angle measure, and you end up with a whole number. You can find the measure of an interior angle of a regular polygon using the equation x equals 180 times the quantity n minus 2 divided by n. And n, in this case, represents the number of sides. Determine whether a regular 16gon will tessellate the plane. Explain. So in order to figure this out, we have to figure out if the interior angle of this regular 16gon will in fact be a factor of 360. So we're going to apply this rule, 180 times the quantity n minus 2 divided by n. N in this case is 16 because 16 is the number of sides of the regular 16gon. In this case, when you follow order of operations, you end up with an interior angle measure of 157.5 degrees. You cannot divide 360 by 157.5 degrees evenly, so it will not tessellate the plane. Determine whether a regular decagon will tessellate the plane. Explain. Teachers, go ahead and pause the video now. So a regular decagon has 10 sides. So in order to figure this out, we're going to substitute 10 in for n in our equation. 180 times n minus 2 divided by n. So x is equal to 180 times 10 minus 2 divided by 10. X equals 180 times 8, because 10 minus 2 is 8, divided by 10. So x equals 1,440 divided by 10, and 1,440 divided by 10 is 144. Because 144 is not a factor of 360, a regular decagon will not tessellate the plane. Not all polygons have to be regular to tessellate the plane. Any triangle is capable of tessellating the plane because the sum of the measure of its interior angles is 180 degrees. Any quadrilateral is capable of tessellating the plane because a quadrilateral can be formed by two triangles. The sum of the interior angles of a quadrilateral is 2 times 180, or 360 degrees. Even though all triangles and quadrilaterals can tessellate the plane, not all polygons can. Only 15 types of convex pentagons and 3 types of convex hexagons can tessellate the plane. If a convex polygon has 7 or more sides, then it cannot tessellate the plane. Will an isosceles triangle sometimes, always, or never tessellate the plane? Describe the transformations that can be used to create the tessellation shown below. So in a previous slide, we learned that any type of triangle will tessellate the plane because the sum of the interior angles of a triangle is 180 degrees. So we're going to look at how this figure was created using transformations. So if we look here at triangle A and B, we seem to see that this set of triangles is rotated about the midpoint of the side they share. So if we rotate it around, we end up with A triangle down here and B triangle here. In order to create triangles C and D, we can actually translate AB along this vector, and it will create triangles C and D. So right now in our figure, we have created this bottom level triangles A, B, C, D. We rotated triangle A to create triangle B, and then we translated A and B to create CD. To create the top part of our tessellation, we are going to rotate around this line. So let's see what that looks like. So when we rotate this bottom 4 triangles around this line, we end up creating the tessellation that will be used to tessellate a plane. A figure has symmetry if there exists a rigid transformation, reflection, translation, rotation, or glide reflection that maps the figure onto itself. Figures that have symmetry are self-congruent. One type of symmetry is line symmetry. A figure in the plane has line symmetry. Sometimes this will be referred to as reflectional symmetry, if each half of the figure matches the other side exactly. When a figure has line symmetry, the figure can be mapped onto itself by a reflection in a line called the line of symmetry, or sometimes you'll hear it referred to as the axis of symmetry. Determine whether each figure has a line of symmetry. If so, draw the lines of symmetry and state how many lines of symmetry it has. In figure A, we have a regular pentagon. It looks like if you were to draw a line from that top point down to the midpoint of the side across from it, that you could fold your shape in half and the two sides would match up exactly. That's actually what happens 5 different times. So what we're going to do is we're going to count the lines that we have. 1, 2, 3, 4, 5. But you notice that this line right here, if I was to count it again, I've already counted it with the number 1. So this figure only has 5 lines of symmetry. And in figure B, it does not appear that we can cut this shape in half and it will match up exactly to the other side. So in part B, we actually have 0 lines of symmetry. Determine whether each figure has a line of symmetry. If so, draw the lines of symmetry and state how many lines of symmetry it has. Teachers, please pause the video and have the students work on this check. So in this check, we see that the rectangle shape has 2 lines of symmetry. We can cut it vertically in half and horizontally in half. So it has 2 lines of symmetry. This equilateral triangle has 3 lines of symmetry, 1 from each vertex to the midpoint of the side opposite. And here, this trapezoid has 0 lines of symmetry because this side on the left and this side on the right do not have the same length. Talk about it. Ask a partner to provide feedback on your work. Are there ways in which you can improve your process that you did on the check? Teachers, pause the video and give students time to talk.